All right, let's take a look at this worksheet from section 3.3. We have a division algorithm which tells us that if we divide a polynomial by the divisor d of x, the result is the quotient q of x times d of x plus the remainder r of x. So that will give the function can be written as d of x times q of x plus r of x. The answer to the division problem is q of x plus the remainder r of x divided by d of x. So the corollary tells us that if d of x is x minus c, r is a constant, and f of x is q of x times d of x plus r. Let's look at dividing x plus 2 into 3x to the 5th plus, we're going to write 0x to the 4th since there is no 4th degree term, and 0x cubed since there is no 3rd degree term, minus x squared minus 7x minus 2. So this is our dividend, and our divisor is x plus 2. And we want to use long division to complete this process. So notice it's important to fill in the missing powers of x. 3x to the 4th times x gives me 3x to the 5th. 3x to the 4th times 2 gives me 6x to the 4th. I'm subtracting, so I can change this to an addition if I change the signs of what I was subtracting. Now I can add. The first addition is 0. The second addition gives me negative 6x to the 4th. Since my divisor has two terms, I want to bring down one more term. So I bring down the 0x cubed. And I repeat the process. X goes into negative 6x to the 4th, negative 6x cubed times x is negative 6x to the 4th, negative 6x cubed times 2 is negative 12x cubed, and I'm subtracting. I can change that to an addition if I change the signs of what I was subtracting to their opposites, and now I can add. So I get a 12x cubed. I bring down the next term, negative x squared, and I repeat the process. X goes into 12x cubed. Notice I want to have two terms since my divisor has two terms. And x goes into 12x cubed. $12x squared times, that gives me my next term in my quotient. 12x squared times x is 12x cubed. 12x squared times 2 is 24x squared. I subtract and then change that to an addition by changing not only the subtraction to addition, but the signs of what was subtracted to the opposite. And now I add to get negative 25x squared. Bring down the next term, negative 7x, and repeat the process. Getting a negative 25x in my quotient. Multiplying that by x gives me negative 25x squared. Negative 25x times 2 is negative 50x. Let's change our subtraction to an addition, which means we have to change the signs of what we were subtracting to the opposite. And let's subtract. We get 43x, and let's bring down that minus 2. So we still can continue the process because the degree of my remainder is still not smaller than the degree of my divisor. So when I divide x into 43, into 43x, I get 43. 43 times x is 43x. 43 times 2 is 86. Let me move that x out of the way. There shouldn't have been an x there. Change the subtraction to addition, and the result when I add is negative 88. And I am now finished. Since negative 88 has degree 0, it has no variable in it, so the degree is 0. And the degree of my divisor is 1. Soon as my remainder is smaller in degree than my divisor, the division is completed. So the answer is the quotient 3x to the 4th minus 6x cubed plus 12x squared minus 25x plus 43 plus the remainder negative 88 over the divisor x plus 2. Now the equation from the division algorithm says the dividend 3x to the 5th minus x squared minus 7x minus 2 is my quotient 3x to the 4th minus 6x cubed plus 12x squared minus 25x plus 43 times my divisor x plus 2 plus my remainder negative 88. So that's what the equation that results from the division algorithm tells me. Well, now let's divide this by synthetic division. And we've got to look at x plus 2 as x minus c. So x plus 2 is the same as x minus negative 2, so c is negative 2. So I put c in this partial box of the synthetic division setup. And now beside that, I write the coefficients of my function f of x. 3, 0, 0, negative 1, negative 7, and negative 2. Since there was no 4th and 3rd degree terms, I have zeros in those positions for the coefficients. Bring down the first coefficient of the dividend, multiply that by negative 2, I get negative 6, add, the result is negative 6. Multiply this by my c, and I get 12. Add that to 0, and I get 12. Multiply negative 2 by 12, and I get negative 24. Add that to negative 1 to get negative 25. Multiply that by negative 2 to get 50. Add to negative 7 to get 43. Multiply that by negative 2, I get negative 86. Add that to negative 2, I get my remainder of negative 88. So the final in synthetic division, when the process is complete, the last number is the remainder. The other numbers to the left of the remainder are the coefficients of the quotient. So notice my quotient is the same quotient as when I did long division. So my quotient has these coefficients. The negative 88 is my remainder. So the quotient is 3x to the 4th, always 1 degree less than the dividend, minus 6x cubed plus 12x squared minus 25x plus 43. And when I add the remainder over the divisor, I get the answer to the division problem. So this is the result of dividing f of x by x plus 2. The same result I got when I did long division. The remainder theorem tells me if a polynomial f of x is divided by x minus c, the remainder is f of c. Using the remainder theorem, if the remainder is 0, then f of c is 0. And that means x minus c is a factor of the polynomial. So let's use the remainder theorem for our function f of x. And we want the remainder when we divide by the binomial x plus 2. Well, the remainder theorem tells me the remainder is when I divide f of x by x plus 2 is f of negative 2, f of c. So the remainder of this division will be f of negative 2. So in other words, we already know that the remainder was negative 88. So that means f of negative 2 is negative 88. So if I hadn't done the division already, to find the remainder using the remainder theorem, I would replace the x's in f of x with negative 2, as I'm doing here. And this result will be negative 88. And you can go through the calculation and see that that result is true. Now you may wonder, why is this true? Well, remember that we get the following equation from the division algorithm. F of x is the quotient q of x times the divisor d of x plus the remainder r of x in general. But when d of x is x minus c, this turns into q of x times x minus c plus r. The remainder always has to have a degree smaller than the divisor. X minus c, if that's my divisor, that's degree 1, so my remainder is degree 0, which is a constant. F of c is q of c times c minus c plus r. Well, c minus c is 0. Q of c times 0 is 0. So f of c then is 0 plus r. F of c is just r. So that's why the remainder theorem is true. If I divide f of x by x minus c, the remainder is f of c. So let's divide our polynomial by x squared plus 2. Since x squared plus 2 is not of the form x minus c, I have to use long division. So I can't use synthetic division on this problem. Alright, so I need to fill in the missing powers. There's a missing power of x in the divisor. I write 0x, and two missing powers in the dividend. So x squared goes into 3x to the 5th, 3x cubed times. When I multiply that by the divisor, I get 3x to the 5th plus 0x to the 4th plus 6x cubed. And I can change that to, I am subtracting, but I can change that to an addition, as long as I change the signs of what I was dividing by. What I was subtracting. So the result is of this addition is negative 6x cubed. I need to bring down two more terms. Because my divisor has 3 terms in it, I want to always be working with 3 terms in this position. So x squared goes into negative 6x cubed 6x times. 6x times my divisor is negative 6x cubed plus 0x squared minus 12x. And let's change that to an addition by also changing the signs of what I was subtracting. And when I add, I get negative x squared plus 5x. And I'll bring down that final term, my constant negative 2, and divide again. X squared into negative x squared is negative 1. Negative 1 times my divisor is negative x squared plus 0x minus 2. Change that to an addition. And add, getting 5x. And the other two sums are 0, so 5x is my remainder. So my dividend, 3x to the fifth minus x squared minus 7x minus 2, is equal to the quotient, 3x cubed minus 6x minus 1, times the divisor, x squared plus 2, plus the remainder, 5x. So that's the equation that comes from the division algorithm. The answer to the division, f of x divided by x squared plus 2, is my quotient, 3x cubed minus 6x minus 1 plus 5x over x squared plus 2. So that would be the answer to the actual division. The equation above is the equation from the division algorithm. All right, and notice that the divisor multiplied by the quotient plus the remainder gives me the dividend. And notice that that is the equation that results from the division algorithm. Let's use the remainder theorem to determine if my x minus c is a factor of my polynomial. And remember, if x minus c is a factor of the polynomial, f of c has to be 0. And if f of c is 0, x minus c is a factor of the polynomial. So x minus c is x minus 3. That means c is 3. So all we need to do to use the remainder theorem is find f of 3. We don't have to actually do the division. So f of 3 is 4 times 3 to the fifth minus 3 cubed minus 2 times 3 minus 5. So that's 972 minus 27 minus 8 minus 5. And this gives me 932. So the remainder, when I divide by x minus 3, is not 0. F of 3 is not 0, it's 932. I can conclude that x minus 3 is not a factor of my function f of x. And that's what the remainder theorem and the factor theorem give me. In this case, f of x is my divisor. All right, let's find the remaining zeros of this polynomial, f of x, given that c equal 1 is a 0 of multiplicity 3. So that means I can divide this polynomial f of x by 1 3 times, and each of those 3 times, actually I'm going to be dividing the first time, and whatever my quotient is, I'm going to divide that by 1, and I'm going to have a 0 remainder in that division also. And notice these are the coefficients of my polynomial f of x, and I'll go through the synthetic division process. And notice I get a remainder of 0, since c is a root or a 0 of the polynomial. Now I'm going to repeat synthetic division where c is 1. This time my dividend is my quotient from the previous division. So notice how I'm writing the coefficients of the quotient. And I'm going to divide again, and I'm also going to get a 0 remainder here because 1 has multiplicity 3. So because the multiplicity is 3, I can perform synthetic division on this resulting quotient, and I'm also going to get a 0 remainder here. And so I knew this would happen since 1 has multiplicity 3. I knew these 3 synthetic divisions were going to result in 0 remainders. So f of x is x minus 1 to the third times 3x squared plus 4x plus 1. Notice these are the coefficients in my final synthetic division quotient. I can factor 3x squared plus 4x plus 1 into 3x plus 1 times x plus 1. And you can check those factors to make sure they're correct. And to factor completely, I need to factor a 3 out of this factor 3x plus 1. 3 times x gives me 3x. 3 times 1/3 gives me 1. And then I'll recopy the factor x plus 1. So now I have f of x factored completely. I put the monomial factor first. 3 is the monomial factor times the cube of x minus 1 times x plus 1/3 times x plus 1 would be my complete factorization of the polynomial. And notice the zeros of this polynomial are 1, which has a multiplicity 3. The power on the factor that gives me that 0 is 3. The next 0 is negative 1/3. That has multiplicity 1. And the third 0 is negative 1. And that has multiplicity 1. So the multiplicities come from the power on the factors that give me the particular 0. So the power on x plus 1/3 is 1. So the multiplicity of the 0, negative 1/3, is 1. The power on x plus 1 is 1. So that's the multiplicity of the 0, 1.